quantum, he is a quantum applications researcher whose work is focused around quantum chemistry for scaling up calculations for both classical and quantum computers. He also has some experience in client engagements within the chemical industry. Today, he will be teaching us about a very interesting and important application of quantum computing, which is simulating molecular properties using variational quantum eigensolver algorithm in Qiskit. Dr. Kawashima, we thank you for joining us at such a late hour. You are welcome.
Can you hear me now? Sorry, I thank you for the very kind introduction, but I have to make a confession. I couldn't connect and share my screen, so I had to move out. So I couldn't hear the lovely introduction that much, but thank you so much for your kind introduction. So I'm gonna share my screen. I assume that you can see my screen now. And yes, and I think now it's in the full screen mode.
Yes.
Okay. So yes, thank you so much. And today it's a great pleasure to be part of this meeting. And I think there's a word molecules. So it's rather related to chemistry. So it might be not familiar for quantum information or quantum technology, but actually it is our fields and the simulation techniques are sort of like focused as a very important application in quantum computing. So today I'd like to introduce you what kind of thing that we can do and what we're up to, and so far what we can do on a quantum computer. And at the very end, I'm going to give some a tutorial about using the Qiskit for chemistry simulation. And I'm not sure that you're that interested that much, but these are the textbooks which is quite familiar in our field. Okay. So first of all, I'd like to briefly explain what can we do using quantum chemistry simulation. So this is an example of a chemical reaction captured in an experiment. The experiment is done using the atmosphere gas phase, and they said that the product, the reactant is this, and the product seems to be this. However, they know only this first part and the last part. It's very difficult to track what's in the intermediate state. So, and also they don't actually know the structure. This is just a guess. So an experimentalist came to me and said, hey, I want to know what's going on. So could you do some simulation to confirm this? So I did this kind of thing. So starting from this, as you can see, it's moving. So it starts from this, you go all the way up here and arrive at this state. So what we did is that not only that we could see the reactant and the product, but we could also find the intermediate states. And also we can calculate the energy barrier that we have to overcome to make this reaction happen. So you can see that simulation can really help to see what you can't see in experiments. Another thing is this is about a molecular property. So excited state energy is an important property because it corresponds to the absorption spectra, which is what kind of light does the molecule absorb. The energy difference from the ground state and excited state will be the wavelength of the light which will be absorbed. So if you consider this beta curtain, I think most of you are familiar with, it's a color of orange. It's in pumpkins. So why it's orange is because it reflects the orange and yellow while it absorbs this blue region. So that's why you can see it as an orange. If you can do this accurately, then for instance, if you can tune this molecule so that you could tune the absorption wavelength, then that means you could tune the light, the color of light, I mean. So by doing that, you can make a new molecule which has an important property which is suitable for your use. So you can see that quantum chemistry could be useful not only for academic purpose in the sense of understanding the chemical phenomena, but also it can be important for chemical industry, like drug discovery, material design, and so on. So this is what we can do. I explain what you can do with quantum chemistry. So then how you do it. I'm going to describe what we do in quantum chemistry simulations and the algorithms. So what we do is, first of all, we solve the electronic Schrodinger equation, which is on your left-hand side. The first term is the kinetic term of the electrons, and the second term is the nuclei electron repulsion attraction, and the third term is electron-electron repulsion. So by solving this equation accurately, we try to predict the microscopic chemical phenomena. And so then I'm going to explain how we actually solve the problem. But before that, I want to mention some of the keywords which is important to understand the quantum chemistry simulations. The first keyword is a molecular orbital. What a molecular orbital is it describes or represents the location of the electrons. So in this case, this will be located around the benzene ring and a phenylalanine molecule. And so in this case, it'll be around a metal in this molecule. So this is a molecular orbital, and there are approximate solutions to the Schrodinger equations for the electrons in the electric field of the molecule's atomic nuclei. And to get the molecular orbital directly from that is very difficult to do so. And by the way, this is the orbital illustration, and these are the orbitals in the energy space. So in each orbital, there's an upspin and downspin, which is alpha and beta. And intuitively, the electrons get into the orbitals which are more stable. So you put in the electrons from the bottom to the top. And as I mentioned, we can't do it directly. So how we do it, we use a method called Hartree-Fock method, which is a mean field method with atomic orbitals to do so. And by the way, today's methods that I'm going to introduce, they're all classified as a molecular orbital theory. So you can see that molecular orbitals are very important to understand this. And to describe the wave function, it is convenient to use a Slater determinant. So for instance, if we have a two-particle system on your left hand, as it's shown on your left-hand side, you can see a product of two orbitals. However, this doesn't work because fermions are antisymmetric, which means if you exchange the first particle and second particle like this, the signs has to flip. So in order to describe that, we describe this as a Slater determinant, as shown like this. So for the n particle, it'll be a Slater determinant like this. Okay, so this is how we show the wave function. And now I'd like to move into how do we try to solve the Hartree-Fock equation and get the molecular orbitals. So here we want to solve it quite simply. So we introduce a model which could make it convenient to solve it simply. So we introduce an independent particle model, which is mean field approximation, which means what we do. So we have the kinetic energy term and the electron nuclear term. So for these, it's a one electron term. However, the tricky part is this term. So it's electron, so they have two electron terms here. So that makes it a bit difficult to solve. So as a mean field approach, we make an approximation like this, which means we don't treat the pair interactions explicitly. What we do is that we assume that each electron feels an average field from all the other electrons. So by doing that, we can solve this we can substitute this with a one electron function. Now it's like this, so it'll be a bit easier to solve. And the actual, by using that, we get to the Hartree-Fock equation like this. So you don't have to understand it in details, just the essence. So this is the kinetic energy and the nuclear electron energy term, but these are the electron-electron contributions. So they're described like this. And the first term is called the Coulomb term. It's the interaction between the different spins. And this has a counterpart in classical world, which is a Coulomb interaction, so a charge-charge interaction. However, in the second term like this, it's called exchange term, and it's an interaction between the same spin terms. However, in this case, it's fully quantum and it doesn't have a counterpart in the classical world. So now we want to solve this equation. However, we cannot solve this analytically for molecules because we want to solve this problem and we want to solve this wave function and this eigenvalue problem, but we also contain this in J and K. So it makes, we can't solve it analytically, so we have to solve it numerically. And to make it simple, we introduce an approximation called a linear combination of atomic orbitals. So we construct the molecular orbitals with a linear combination of atomic orbitals like this. And introducing that, this equation becomes like this. But maybe it's a bit difficult, so I want to explain it again in an illustration. So what I mentioned is that we make or construct a molecular orbitals using atomic orbitals. And we make it by the linear combination of these atomic orbitals and make these. So from hydrogen atom orbitals, we make hydrogen molecule orbitals like this. And then how we describe atomic orbitals. I'd like to explain that in the next slide. And so the atomic orbitals are usually called as basis sets. For chemistry problems, we could use a lot of different kind of basis sets. For instance, plane wave basis, they are very good at treating the metallic systems, or like wavelets, or it could be a real space grid. But in isolated molecule quantum chemistry simulations, we frequently use these Gaussian basis sets. So we describe these atomic orbitals with these Gaussian basis sets. So by the way, this Slater type orbital like this is the sort of like the accurate description. So this is better in accuracy compared to the Gaussians. However, Gaussians are used because the integrals are easy to calculate. So these Gaussians are mimicking this, and we use this because for the computational reasons. So we use those Gaussian bases here, and we solve this problem. And to solve it, we usually use a matrix representation, which makes it called the method, the Hartree-Fock-Rotan method. So these are described as this in a matrix, and this is also described in a matrix like this. So it'll be this problem will now be to solve this matrix problem. So to get the eigenvalue of this. So as again, we have to solve this numerically. So we solve this iteratively because the C is also included in this part. So we have to solve this iteratively and optimize this C to get the molecular orbitals. As we mentioned, we're doing this because we want to get the molecular orbitals. So we are optimize this C. So what we do is that first we start with 3D coordinates of atomic nuclei and also determine what kind of atomic orbitals we use to describe the molecular orbitals. Then we construct the initial guess of the molecular orbitals, and then we go into the loop. We construct the Fock matrix, the F matrix you see on your left-hand side, and then we diagonalize it. So then we get the eigenvalues. If the wave function or the molecular orbitals are converged, we get the orbitals and their energy, and we repeat. We go back to 3 if it's not, and we continue this until we get the convergence. So this is how we calculate the Hartree-Fock. So by solving this Hartree-Fock calculation, we construct the molecular orbitals from the atomic orbitals like this. And so now we get this molecular orbitals. So finally, I wanted to mention one thing about the Hartree-Fock method. So Hartree-Fock method, how accurate it is. You can see that it's 99% accurate. So there's only 1% error in the total energy. So maybe it seems that the error is small, so it seems to be accurate. However, there is a problem. For instance, if you consider this Si to H2, they have a lot of isomers, which means a lot of stable structures. So, and they did some in the past, some researchers did some calculations and found that these 4 are the most stable structures. However, Hartree-Fock cannot obtain this. So what that means is that 1% seems not be a big deal. However, the 1% might be important, not just quantitative sense, but also in a qualitative sense. You can't describe this. So that means that Hartree-Fock is doing a good job, but you have to do better. So from the next slide, I want to explain how we go better beyond Hartree-Fock. So I think this is the first checkpoint so far. So I want to ask that if there are some questions. Oh, is it okay if I pass it on to you, Sabadia?
Yes. I don't see any questions in the chat right now, so I think we're good to move ahead. Please continue.
I see. Okay. Thank you. Okay, so as I mentioned, Hartree-Fock is doing a quite well job. It calculated quite accurate energy, and we were able to produce the molecular orbitals. But we have to do better. So how can we improve this Hartree-Fock method? So in the energy sense, we want to get this correlation energy, which is the difference between the exact energy and the Hartree-Fock energy, as much as possible. And we want to do this in a very efficient manner. So in the next few slides, I want to explain how we do that in general. And there are usually 3 different approaches to accomplish that. There's perturbation theory and configuration interaction and coupled-Luther methods. Today, I will focus on the latter 2 methods. Sorry. Okay. So before that, I want to describe about what kind of Hamiltonian we're going to tackle. And also, I want to describe this second quantized representation because it makes it easier to describe the next 2 methods that I'm going to explain. So second quantization picture is starting for the molecular orbitals. So we could consider the second quantization after Hartree-Fock. So we consider Fock space. So each Slater determinant, like this, is represented by an occupation number vector, which means rather than describing the spin, so what we do is we quantize the field. So rather than describing it in the spatial distribution. So what that means is that, for instance, this is its Slater determinant. So we describe each part with zeros and ones. So it's describing whether that orbital is occupied, which one, or not, which is zero. So you should have the number of ones as the number of the electrons. And we introduced two new operators. So the creation operators is you create a orbital like this, or annihilation operators, you remove this orbital. So by introducing these two operators, we can construct the Hamiltonian in a second quantized form. So the Slater determinants of n electrons can be created from the vacuum. The vacuum has nothing in it. And by using these creation operators, we can construct the Slater determinant of n electrons. And using the creation and annihilation operators, the second quantized Hamiltonian is described like this. This first term is the kinetic and the nucleus electron repulsion terms, like this. And also the second term is the electron repulsion term. So this is the Hamiltonian we'll tackle. So now I'd like to describe the first method, which is frequently used to calculate the correlation energy to improve the Hartree-Fock results. So what we do is quite simple. So this is the Hartree-Fock Slater determinant. We can describe the wave function is a linear combination of the Slater determinants like this. So this is the Hartree-Fock, which is like this. So as you can see, the electrons are put in from the bottom to the top like this. So this is the most stable electron configuration. And then we consider this term, which is the single excitation term. So there's one electron exciting. So in this example, it's exciting from there's an excitation from this orbital to this orbital. Of course, there's from this to this, and there's all sorts of that, but they're all single excitation terms. So they're also describe the combinations of them, and also double excitation and triple excitation, and so on. So for n electron systems, we could consider up to n excitation terms. So if we calculate all that without any truncation, it is exact. It's called full CI, full configuration interaction, or in physics, it'll be called an exact diagonalization. However, we usually truncate the CI terms because it's too computationally, it's computationally demanding. So what we do is for instance, this is an example of we truncated up to the double excitation terms. It does a quite well job. However, there is a drawback in this method. Assume that we have two molecules, two atomic molecules like this, a molecule like this. So this A and B is very far from each other. So then usually the energy of these two atoms together should be an addition of this and this, right? Because if we expand it, and if it's so far away, it don't feel each other anymore. So there should be no interaction. So this should be fulfilled. And this will be fulfilled if we don't introduce any truncation. So it'll be exact in the full CI. However, if we truncate it up to doubles, it'll be like this. It won't fulfill this condition. Because the reason why is that you can see it on your right-hand side. So if you consider these terms up to singles and doubles, and these terms up to singles and doubles, what kind of excitation will be when it's in this entire system? So you can consider up to singles and doubles here and singles and doubles here, but you can also consider up to singles and doubles here. However, to describe these, you need a triple excitation. And to describe this, you need a quadruple excitation in the full system. That is the reason why if you truncate it up to doubles, you can't describe this. So that's why it won't be equal here. Well, it seems not to be a big deal, but it is very important because when you try to describe a chemical reaction, what you do is you form or break bonds. So what this is saying is that there will be trouble when you break the bonds. So in practical sense, it is not that useful. So that is why the researchers came up with a new idea, which is called the coupled cluster method. So previously, we were just doing the linear combination of the later determined terms, but now in this case, we are putting these excitation terms into the exponent. By doing so, now we could describe A and B together will become AB will be A plus B when the A and B do not interact. So by using this exponent terms, we can now describe the bond breaking and the bond forming accurately. So that is why the coupled cluster is frequently used in quantum chemistry simulations. So I've described what's the configuration interaction and what coupled cluster is very briefly. So now we were at 99% of the total energy at Hartree-Fock. How much we improved? The CISC I was mentioning, the CI configuration interaction, it can take into account the remaining 90% of the last 1%. And for the coupled cluster, you can go up to 95% or more of the last 1%. Yeah, we're doing a good job now. However, you have to see the right-hand side. So these blue terms are the scaling against the system size. So Hartree-Fock is up to n to the power of 2 or 3, which is not that bad. But to get the remaining of the last 1%, you have to make a large effort here, like n to the power of 6 or n to the power of 7. And I maybe explained about the configuration interaction without truncation. That's full CI, so that's the ultimately accurate method. However, the computational resource for full CI grows exponentially. So when we try to tackle large systems with these methods, we need a huge classical computer, which is usually a supercomputer. However, for instance, if we can calculate this size in this current supercomputer, we have to build a huge computer to calculate a 2 times larger molecule. So you see, it doesn't scale well on a classical computer. So that's why, from the quantum chemistry point of view, we need a better solution. So that's where the quantum computers come into the picture. So currently, what we're trying to do is as follows. We do Hartree-Fock calculation on a classical computer because it scales well, scales not bad. But for the remaining, this ill scaling, we want to solve this problem. So for now, we want to consider to compute this on a quantum computer. So from the next slides, I want to explain how we try to do that on a quantum computer. So this part is the end of the introduction of quantum chemistry methods on a classical computer. Is there any questions?
Yes, we have two questions. I would read them out to you now. The first one is, what are the criteria for a molecule that it would hold good at Hartree-Fock equation, as you have shown in the slide where you have mentioned about the H2SI2 molecule?
Okay, first of all, I'll go back to some slides. I'm very sorry, but could you repeat the question again?
Okay. The question is, what are the criteria for a molecule that it would hold good for the Hartree-Fock method?
What are the criteria for a molecule that it would hold for Hartree-Fock equation? So what are the criteria for a molecule that it would hold good? So I think what this is saying is that what kind of molecule will be suitable for Hartree-Fock and you don't have to do more? Is that the thing?
Yes.
I see. Okay, thank you. So maybe I should go another slides. Okay. So first of all, I'm sorry, I'm going back and forth. Sorry about it. So to describe the electron configuration as a single determinant or one electron configuration, that part, it works for many systems actually, because especially when the bond is very stable, then the Hartree-Fock will relatively do a good job. However, what we need to do is, for instance, we have to calculate the energy difference from this. So for instance, we want to calculate the barrier like this to overcome this reaction. So it'll be a subtraction of this part and the energy. But for this, usually Hartree-Fock method has a lot of errors. And couple cluster methods will be a bit more accurate, but it seems to be small. But when you subtract the energies of two, then the difference becomes more larger. So first of all, it's difficult to mention about what kind of criteria is good, but when we consider those kind of things, Hartree-Fock is sometimes shortcoming with it in general. And also, another example is when you, there is not a good example. Okay. Oh, yeah. Sorry. Yes. Sorry, this part might be a good example. As an example, I mentioned that this you make these two atoms far away, and so this is describing the bond breaking, bond forming. But when you try to describe this little by little, usually Hartree-Fock will break down. And I have an example to show you today, and a Qiskit example. So we could come back again in that tutorial session of the Qiskit. Sorry for the long answer, but this is my answer so far. Is it okay, or thank you. Then the next question is?
The next question is, can you give an example of largest molecule that has used CCSD or Hartree-Fock method to give sufficiently accurate results?
I see. So for couple cluster systems, I've seen an example of two molecules which were aligned like this. So what they're doing is trying to describe an interaction between a graphene sheet. Do you know what a graphene sheet is? Okay, sorry, I'm going back and forth so much. Okay, so this is a benzene. So it's like a honeycomb, and there's a sheet which is continuous with these honeycombs, and so it's like how should I say a sheet before making it into a tube or something like, because a carbon nanotube is a very important system for nanomaterials. So it's trying to understand what's the basic property of them. And also, they're also, I think the graphene sheets are probably important for trying to get superconductivity. So to understand those kind of physical behaviors is important. And I think the quantum chemistry simulations were trying to tackle that. And what I've seen is that trying to get a small portion of that and try to calculate the interaction energy between them was the largest. So it's like maybe like 40 or 50 carbon atoms, and 2000 basis functions was probably, I think, the champion. Sorry for the long story again.
Thank you. We have another question. This is the last question we'll take before we move on to the next part. The question is, what is the usual speed up that quantum algorithms provide over classical algorithms? Are there any NP-complete problems in quantum simulation of molecules? The complexity of, okay, we can get
so no, please go ahead. No, please go ahead first, sorry.
The complexity of CCSD and CASD was polynomials as shown in your last slide. So why can't we efficiently do them in a classical computer?
So first of all, you're right. And okay, so to first of all, to calculate the full CI without truncation shown here. So we calculate up to n excitations. That'll be exponential. So ultimately, we wanted to solve that kind of problem. But so far, we haven't done that for a very large molecule. So that's why practically right now, what we're doing is trying to solve the couple cluster part efficiently. But so again, the ultimate goal is to try to calculate this full CI, very accurate calculation. So that's sort of the problem we're looking for on the quantum simulation. Am I answering your question, or am I just making you confused? I don't know if you got it, but okay.
Okay, I think we can move on to the next part of the session.
Okay.
Thank you for answering the questions so far.
Oh, no. First of all, thank you for asking. So next, I'd like to move on to the quantum chemistry on a quantum computer now. So what's the advantage of quantum computing in quantum chemistry? So there's two important advantages. The first advantage is that we could explicitly maintain the full many-body wave function. And the second advantage is that it has an ability to propagate the wave function in time by general matrix vector multiplication. So first, I'd like to describe the first advantage. So we go back to the Slater determinant, And we're in the second quantized form with Fock space, so that's why the Slater determinants are described with only zeros and ones. So if we consider classical n bits, we could maintain one Slater determinant. However, if we have the same number of qubits, now, as you can see, we could store a combination of so much Slater determinants, like the full CI wave function. So as you can see here, there is a huge advantage using quantum computer. And then the next advantage was propagating the wave function in time by general matrix vector multiplication. So the propagating the wave functions is important because we could trace the dynamics of the molecules using this method. However, naively, it's too memory intensive. So it's very difficult to do it on a classical computer. Of course, there's a lot of algorithm trying to overcome it, but it's still a different task to do so. However, on a quantum computer, you can maintain a highly entangled quantum state and you could realize unitary evolution like this. And you could avoid the dynamic sign problem, which is crucial in the classical algorithms. And it's usually, it scales exponentially against the system size, but now using quantum computers, it could be polynomial. And advancements of algorithms makes it even more scalable. So now, unlike the exponential scaling, we have a polynomial scale. However, a Hamiltonian simulation hasn't, there's no practical Hamiltonian simulation done so far, but rather these are used as a subroutine of the next algorithm, which is the quantum phase estimation algorithm. A quantum phase estimation algorithm is an algorithm to compute the eigenvalue as a phase of a unitary operator. So in a quantum chemistry, the unitary operator is a Hamiltonian, so the eigenvalue will be the molecular energy of it. So using the Hamiltonian simulation, the eigenvalue of the Hamiltonian could be obtained in a binary representation of the phase. And then by doing that, we could calculate exact energy, which is the full CI energy. Yeah, this is what we were looking for. So, and Asper Guzik, which is a giant in the field of quantum computing and quantum chemistry, did a simulation in 2005 using this quantum phase estimation for the first quantum chemistry application. They performed the first quantum chemistry simulation using this algorithm, this phase estimation algorithm, where the circuit is described like this, and this part is actually using the Hamiltonian simulation. So it's using the second advantage of the quantum computer in quantum chemistry. So as again, we could do this and get the full CI or the very accurate result in a polynomial scaling. While in classical computer, it'll be exponential. So now you can see a huge speed up using a quantum computer. So maybe it's related to the last question. I don't know if I answered it correctly, but so this algorithm shows that exponential scaling on classical computer could be reduced on a quantum computer. However, it's still difficult to do so in the current form of the quantum computer, because the current computer is called a near-term quantum device, which has errors and it's not perfect. It's still how should I say? It's still not perfect. And for the practical simulation, the two methods, the Hamiltonian simulation or the quantum phases simulations that I mentioned, it requires a fault-tolerant quantum computer because they need a long coherent time to maintain the quantum state. Because if you trace the time using the Hamiltonian simulation, you have to keep the quantum state as long as the simulation continues. And also, using the Hamiltonian simulation with quantum phases simulation, you need a very deep circuit. So you need the fault-tolerant computer to do so. But fault-tolerant quantum computers, what that is that you need a quantum error correction, which requires a huge number of qubits. And you need a very long coherence time with precise gates and stable qubits, which is not the case in the current status. Rather, our near-term quantum devices has limited number of qubits, and it has a relatively short coherence time, and it still has noise from environments. So in order to do a useful simulation on the near-term quantum device, we need a better strategy to accomplish that. So in this near-term device, what we try to do is that we use a variational quantum eigensolver to tackle the chemistry problems. So I'd like to first explain what kind of workflow is, I'd like to explain the workflow of this variational quantum eigensolver. So first, you have a molecular Hamiltonian. So again, you solve the Hartree-Fock, you can get the molecular orbitals, and you construct the molecular Hamiltonian. And then what you do is that you need to transform a fermionic Hamiltonian in a qubit Hamiltonian. So you use a mapping to do so. And then you construct a circuit, and then you perform a variation quantum eigensolver, and you get the energy. In the variation quantum eigensolver, you use two different types of computer, which is a classical computer and a quantum computer. So you first propose a circuit for trial state on a quantum computer and measure the Hamiltonian terms, and you estimate the energy. And then you update the parameters using classical optimizer on a classical computer. So I'd like to describe this process more briefly, more carefully. Oh, sorry. So first, as I mentioned, we need to transform the fermionic Hamiltonian in a qubit Hamiltonian. So we use a mapping to do so. And Jordan-Wigner mapping is one of the most frequently used mapping. So I'd like to describe how we map it using this Jordan-Wigner transformation. So in the second quantized Hamiltonian, as I mentioned, there is a creation operator and an annihilation operator described like this, and the Hamiltonians are described like this. So for each term of this, we substitute these into this. And we reformulate it and add up with the linear combination of these spin terms, or the Pauli terms. So what we do is we transform this into this. And by doing so, we could we could map it on a quantum, we could map it on a qubit. And next, we want to create a circuit. And this is a couple cluster method that I previously shown, but it's truncated into singles and doubles. So this couple cluster singles and doubles is frequently used. However, this is not unitary and it is not variational. So we can't use this directly on a quantum computer as we did on a classical computer. What we use is a unitary invariant of the couple cluster method. So what's different is we have a de-excitation term like this, a dagger, not with this excitation term like this. Now, if we do that, it's unitary now. And more better, it's variational now. So we could use this on a quantum computer and compute the molecular energies and so on. Well, I would like to briefly explain another advantage. So if we want to implement this unitary coupled cluster on a classical computer, because of this term, we need to truncate a term to realize the program to run on a classical computer. So we need to truncate it, and what happens is then that we lose all the advantage of the unitary coupled cluster. It's not variational anymore. However, we could easily implement this on a quantum computer. So it's not a real quantum advantage, but there is an advantage of doing the computation on a quantum computer for this unitary coupled cluster. So we'll use this unitary coupled cluster as an ansatz to construct a circuit. So what we do is that we construct the circuit to prepare the state. And this is the equation that I showed you just in the previous slide. And these are the singles excitation terms in this creation and annihilation form, and this is double excitation. So, and we trotterize the circuit, we trotterize this, and then by doing each term, we get these C0 gates. So we construct this circuit and we use this to prepare the state, the quantum state. So I'm going to review the VQE of variational quantum eigensolver once again. So first, we prepare a quantum state on a quantum computer, this part, and we optimize this parameter on a classical computer using classical optimization. So we prepare the state using the ansatz. I've just shown the UCCSD ansatz on a quantum computer, and we run it. We run the circuits and prepare the state, and we measure it. And we calculate the energy, and then we optimize a parameter on the classical device, and we go back again. And we repeat this procedure until the convergence criteria is met. So this is the variation quantum eigensolver. So we're going to run this variation quantum eigensolver on simulation using variation quantum eigensolver on using Qiskit. So we're going to mostly use Qiskit nature among the many different Qiskit programs available. There's Air, Terra, and so on, but we're going to mostly focus on nature here. So it can solve many problems like fermionic problems and spin problems, and also vibrational Hamiltonians to calculate the molecular vibration very accurately. And I'll mention this again, but we need an external program to do the Hartree-Fock calculation to prepare the molecular Hamiltonian, which is necessary for the quantum simulation. So we support various programs to do so. And we have we support these kind of mappers from fermion to qubits. And we have algorithms to solve the ground state, not just the ground state, but we could also solve the electronic excited states as well. And I'd like to explain the workflow of the quantum chemistry calculation we do today. First of all, we calculate the electron integrals and perform the Hartree-Fock calculation. And then we construct the second quantized Hamiltonian, and then we map it from the Fermionic Hamiltonian to the qubit Hamiltonian or the spin Hamiltonian. And then we enter the variation quantum eigensolver. We do the quantum state prediction using ansatz, and then we measure it, and we do the classical optimizations in the parameters, and we repeat this until the convergence criteria is met. And again, as I mentioned, for the first step, we need an external program. And then for the second part, we use Qiskit. So, okay, yeah. So I have prepared 3 sets of examples in a new Jupyter notebook that I'm going to share after a few slides. So first, I have a base calculation setting with a hydrogen molecule with a VQE with UCCSD ansatz. And then I construct a potential energy curve of the H2 molecule, which describes a bond breaking forming. And I'll describe to you what we do later on. And then finally, I show you an example of reducing the computation cost of the quantum chemistry simulation. The first one is changing the ansatz, and the second one is changing the active space. And I think I need to describe what we actually do for the third example. So changing the ansatz. So we have, and Qiskit supports different ansatz of the couple cluster family. So this one is called the UCCSD. So we treat all single excitations and all double excitations. And there's 2 variants of this in which is supported in Qiskit. One is the pair UCCD calculation. We only consider double excitations, which are pairs. So there's in UCCSD, we could treat double excitations with this as shown here. These 2 go to a different orbital. However, for pair UCCSD, these always go to the same place. So that's the pair excitation. And for this second one, which is singlet UCCSD, you consider a single with only one of these, which means there's 2 different there are 2 sets of excitations. So the up goes here and the down goes here, or the up goes here and down goes here. Energetically, it should be the same. But here, we only consider one of them to reduce the computational cost. So by doing that, we lose accuracy a little bit, but we gain a lot in the sense of reducing the computational costs. So it's the accuracy versus the computational cost. And for an active space, well, we reduce the active space. What that means is, for instance, this is the full system. But in the chemistry, the electrons, which are unstable, and these orbitals, which are stable compared to these orbitals play a key role in the chemical reaction. So we can reduce the problem size by including only the important part. We have an error in energy, but sometimes this works to describe the molecular property or chemical reactions qualitatively. So I'll show you these 2 examples in the Jupyter notebook. So, okay, so now I think I need to move on to the Jupyter notebook. Is there any questions before we go into the Jupyter notebook?
Yes, there is one question, and I believe it is in reference to the VQE overview that you showed a few slides ago. And the question is, how do we decide the initial parameters?
Oh, yeah, okay. here, right? But actually, that's a great question because if you can consider a way to make a good initial guess for a general problem, that is awesome because actually we suffer from that. And from quantum chemistry perspective, there is some ways to do it. So for instance, there is an easy way to calculate we can calculate the Hartree-Fock, and then we can use perturbation theory to easily calculate the difference to improve the Hartree-Fock result. And we could use those parameters as an initial guess to solve the couple cluster. That actually works quite well. But in general, to come up with an idea to get a good initial parameter without sweating, that's very challenging. I think it's a great question, but sorry, I don't have an ultimate answer at this point.
I think that is the only question we have. We can move forward.
Okay, sure. Then, okay. Can you see my screen now? And is it showing the Jupyter Notebook?
Yes.
Okay, thank you. So now I'd like to move on to the Qiskit tutorial. So what we're trying to do is trying to use a variation quantum eigensolver I just introduced to solve a quantum chemistry problem. And note that I use a simple environment from Miniconda, and I tried the default installation using pips install Qiskit and pip install Qiskit nature and pip install PySCF, because we're using PySCF as the electronic structure solver for Hartree-Fock. However, I face an issue that I need to lower the version of H5PY, which is necessary for PySCF. So now currently it's version 3 point something, but I have to lower it to version 2. So that's a heads up. And so first I'd like to start from the basic VQE calculation. So first I import the basic libraries of Qiskit, and then I import libraries related to VQE here and nature libraries like here. So initially what we do, we set up the molecular data for simulation. And here, as you can see here, it says PySCF. So we're going to use an external program to do so. Just want to let you know that we're using an interface from Qiskit, but from Qiskit, we're calling a PySCF a program to get the Hartree-Fock energies and so on. So, but first, what we do is we set up the molecule like this. So we need the data for the atoms like this. So this is a 2-hydrogen system. So we have 2 H's, and we need a Cartesian coordinate to determine the position of the nucleus. And then we set the charge, which is 0. It's a neutral here. But if you want to change the number of electrons, like to make it an ion, so +1 will reduce the electrons, and -1 will increase electrons. And multiplicity is 1, so 1 is singlet. So we're solving a singlet state, but we could also calculate doublets and triplets if you want. And here, we need to set the basis sets here. Maybe you're not familiar with names, but there's a lot of basis sets you can actually choose. But here we're using SDO3G, which is a relatively small basis set. So this is the intersetting of the molecule. And then here is where we call the PySCF program via the interface of Qiskit to calculate the Hartree-Fock calculation. And then we calculate Hartree-Fock, and then here it constructs the second quantized Hamiltonians in the molecular orbital form. So it's described like this. Next, we need to map it so that we map it to qubits so we could construct a circuit. So here, there's a qubit converter, which maps it into Jordan-Wigner. I'm using Jordan-Wigner right now. And this is the qubit Hamiltonian we obtained from Jordan-Wigner mapping. And I want you to compare it with the following. So I also used a different mapper, and I reduced the 2-qubit reduction based on the conserving of the number of particles. So here you can see that the 2 qubits are reduced because these are 4-qubit problem, but now it's reduced to a 2-qubit problem. By doing so, you can see there's just a large reduction in the computation. Initially, before doing the VQE, we use a NumPy minimum eigensolver to get the exact reference value. And so we set the solver here and we calculate the ground state energy and get the results. So this is the energy and spins and dipole moments we get here. And now I'd like to move on to the actual VQE simulation. So for VQE, what we do is that we set the optimizer like this. So we're using SLSQP, which is the default of Qiskit, I guess, but we could use Kobila's LBFGSP or other methods. And we set the number of spin orbitals. Here we're using Jordan-Wigner transformation as an input. So this is a 4-qubit problem. So we have the number of spin orbitals as 4, and we set the number of particles, which is hydrogen. We have 1 electron for hydrogen and another electron for another hydrogen. So it's a 2-electron system. So we have this parameter, and we tuck in to get the Hartree-Fock state. So we first prepare the state of this form. So it's a single Slater determinant. And then we use the UCC-SD ansatz to prepare the state more accurately. And now we have the initial part and ansatz. So we tuck them in as a parameter for the VQE solver like this. And here we use a state vector simulator as a backend. And now we could use this solver and solve the ground state and get the energies. Well, you will probably, if you do it on your own, you can see that it'll be very close to or precisely same as the exact results because UCCSD ansatz with 2 electrons will be exact. So this is the basic way to do so. And the next thing is to construct a potential energy curve. What we're going to do is we have 2 hydrogen atoms, and we're going to change the distance little by little and to see how the energy behaves. So here we're changing the length from HH distance from 0.5 to 2.5. And while we change the bond length little by little, we construct the H2 coordinates like this in the same settings here. And the basis, we changed it a bit, but this isn't a big deal, but I just want to change the basis at once. And the next remaining is similar. We use the electron structure problem to put it into PySCF and calculate the Hartree-Fock energy, Hartree-Fock and so on. And then we map the fermionic Hamiltonian into a qubitized form. And we choose the state vector simulator for the backend again. And this time we use a VQE UCC factory, which is sort of like a more of optimized thing where you don't have to set the number of particles and so on. Maybe this is easier. And you use this to solve the ground state and get the results. And finally, you get the Hartree-Fock energy and the couple cluster UCCSD energy like this. And so we're going to draw a potential energy curve of these two energies. And so we use those results and use matplotlib to make the potential curve like this. So the black line is the Hartree-Fock, and the red line is the unitary couple cluster. As you can see, they have a different behavior. So for instance, if you make this distance little by little, and if it's very far away, it should feel no interaction. So what that means is that if you make the distance little by little, it should converge to a point. So it will be flat at the very long distance region. That happens when you use couple cluster, but it doesn't happen when you use Hartree-Fock. So I think there was a question that what kind of place where Hartree-Fock is okay or Hartree-Fock is not okay. So Hartree-Fock is quite okay around in this region, but it doesn't work in these regions. I hope I'm answering the question more efficiently now. So this is the potential energy curve. And the final example is reducing the problem size. So before that, in order to feel how much you're reducing the problem size, well, as a reference, we start from the full size problem. By the way, it'll take a bit longer than the other simulations, so it's a heads up for that. And first, so what we do is we define the molecules like this we did previously. The difference is here. Li is, we change H to Li to make the size a little larger. And then the remaining is mostly the same here. The difference here is probably the difference number of the spin orbitals and the number of the electrons. It's a 4-electron system now, and we have 12 spin orbitals. And we initiate the state from the Hartree-Fock, and we use the unitary couple cluster ansatz. And then we use the VQE, using them with the state vector simulator. And we run the calculation and get the ground state energy, and the results will be shown. So we're comparing the Hartree-Fock energy here and the UCCSD energy here. So you see a difference here. So it's minus 7.7 is now minus 7.8 something. And this time, this is the reference energy, which is the very exact energy. So it's minus 7.8237. And it's 82367. So you see UCCSD is quite accurate. There's a little bit of a difference, but it's mostly the same. Okay, now we change the ansatz. So almost everything is the same here, but the difference is here. So originally it was UCCSD, but now it's pair UCCD. So we only consider the double excitation with pairs. So that will reduce the problem size and make the circuit shallower, because we're using a simpler ansatz than the full UCCSD. Then the remaining, we do the exact same thing, and we come up with the energy like this. And the final simulation is reducing the active space. So we're going to reduce the problem size, original problem size, to this small molecular orbital space. So this is quite different. So first we run the PySCF simulation, and then we use an active space transformer so that we could change the problem size. So we need the information of the number of electrons and the number of orbitals. So this should be 6 as a full size problem. So we're reducing it to 3. And here I'm using, oh no, this is Jordan Wigner mapper, sorry. And so the number of spin orbitals is changing. So it should be 3 times 2 here, so it's 6, and the number of electrons haven't changed. And the remaining is all the same here. And we finally get the energy like this. And by the way, so I've listed all the results here. So starting from Hartree-Fock, and the last one is the exact energy. You see that UCCSD, PUCCD, and UCCSD with active space. So you can see that minus 7.8237 becomes a little bit higher, 6. And then you see quite a large difference in the energy here. And also, this will be more close to the Hartree-Fock energy because we're limiting this problem size. So, but if you calculate it on your own, you can see that these simulations were way faster than this full system size problem. So if you have a chance to change the parameters little by little, probably you could observe the reduction in the computation, which will probably end up with a shorter simulation time with the difference in the accuracy. So probably more effort, you have better energy. So this was the last part, but is there any questions about this Jupyter notebook? Maybe I went too fast, so if you need more explanation, I could do so, but.
I see a question in the chat.
Yes.
The question is, how can we make sure that our choice of ansatz is good for a given molecule?
So first of all, is it about this Jupyter notebook, or do you think this is a general problem, general question?
I think it is a general question.
So first of all, we actually do this kind of thing. So when we want to tackle a large size problem, we usually choose a relatively smaller size problem with a similar chemical character. And then we calculate different ansatz or like changing the active space and see the performance. And then if we find a well spot that we could reduce the system size and we don't deteriorate the accuracy that much, I think that's sort of the spot that we want to tackle. So based on those kind of experiments before we choose the ansatz and tackle the large molecules. Am I answering your question? Thank you. Thank you for asking. So again, so what we did here is actually sort of like what we do practically as a quantum chemist.
I think those are the questions for now. If there are any other questions, please feel free to put them in the chat, or you can also unmute yourself and directly ask the question.
Sure, please, Lisa.
I have a small question.
Yes.
Yeah. So, see, is there any pattern? Namely, we were trying to, apply this, and it seems to work for example, H2, but doesn't work for other things. Is there any sort of systems where correlation is small, where this method will work? If the correlation is stronger, it may not work. Some intuition there.
I'm not sure if I understood your question accurately.
Let me point out, be more specific. For example, H minus, we tried H minus. H minus, as you know, is a very classic kind of example where it sort of failed very miserably. So, H minus, probably because there are a lot more correlation. Maybe the Coulomb part is very strong, it didn't work. EH2 gave reasonable answer.
I see. So are you talking about the accuracy you get?
Yeah.
Is that
exactly.
what you're?
Yeah.
I see. So what was the target? So how did you sort of like judge that if it was accurate? It was the molecular energy or something, or
yeah,
what did you actually?
Comparison with energy. Yeah.
Mm-hmm. So you calculate the energy with what was the reference? So what's the reference value and what's the method? Is it a different method or for H minus?
H2.
Yes.
H2, it is already available. There are some experimental data, with which we could compare, and it was reasonable. H minus, we took from this ARP Rao's paper. He had a series of papers. He has been working on this H minus for quite some time, and then there are some experimental results. There are two closely spaced excited states and one ground state. So we could go to 3 states, but energy difference was quite big. It just didn't convert.
Well, there's many things that I could think, but yes. So one thing you could try. By the way, did you try you on a like using a Qiskit, or did you just use?
Yeah.
I see. Then, well,
maybe we can discuss privately. I'll send you our results.
But yeah, sure. But one thing that maybe changing the space set is important because when it's H minus is I think an anion. So then what happens is that it becomes delocalized.
Correct.
So you need more basis to describe the sort of like the delocalized distribution. So that's one thing.
Okay. So I've been in touch with you because we are working on it.
Okay, sure. Sure. Please, thank you.
I think we do not have any more questions. Dr. Kawashima, do you have anything else to share within this notebook?
So yes, I think I've gone through all this, and yeah. So maybe I think maybe in the Jupyter notebook I've shared, and in the same directory there's a README. So if you see the README, probably you could get an idea of what kind of version I have installed, because I think we have a lot of development going on in Qiskit. So maybe if the version changes, it doesn't run in the manner I've showed you today. So just for the heads up, please be careful for the version. So is there? So maybe then finally, yes. So this is last slide. So I just wanted to then start wrapping up what I did. So, well, first of all, I described like what can we do in general using quantum chemistry simulation. And then I described how we actually solve it, but it was quite brief, but I tried to give you some kind of an idea of what's going on. And then I mentioned what kind of things is difficult on classical computer, which can be doable on a quantum computer. And I've described some algorithms for quantum computing. And finally, I gave you a sort of like tutorial session for running the quantum chemistry calculation using Qiskit. So yes. And finally, so today I was rather speaking on the application side, but actually quantum chemistry researchers were delighted when quantum computers arise because we were facing the ill scaling size problem. So for this, it's a new hope for us. But you saw today that we're still working on molecules of H2, LIH, so it's still small, and there's so much things that we could do to make it better. So I hope gifted people like you who's listening to the tutorial today can contribute so that I could do a larger simulation. So that's it for today. Thank you so much.
Thank you, Dr. Kawashima, for your very lucid tutorial and presentation. For the participants, I would like to thank you for your enthusiasm throughout this session. We would love to hear your thoughts. I have shared the tutorial notebook link. I'll be sharing an additional form and a link to join the Qiskit Slack wherein you can post your questions further on. Please feel free to contact us or Dr. Kawashima if you have any questions regarding this tutorial. Now I would like to ask Professor Panigrahi to conclude the session. I think there is some connection issue from his side. So I would like to conclude the session on his behalf.
Busy, so we would like to thank him and thank you, Sabhyata, for this wonderful session.
Thank you once again, Dr. Kawashima, and thank you to all the participants.
Thank you so much for your time. Thank you.